Hi, my name's Hugh Breslin with Microchip's FPGA Business Unit, and I'm going to be presenting today's session on hard real-time versus high-performance real-time. So throughout the session, we're going to have a look at hard real-time versus high-performance real-time, and firm and soft requirements in high performance, and we'll also have a look at the different ways we can achieve real-time and complete tasks within deadlines in different real-time systems. So let's get started and have a look at hard real-time. So we've got a few different examples that we're going to use throughout this session, and the first one we'll use for hard real-time is an autonomous car driving along. So I have this represented in pictures in a second as well, but if we think about it, where we have an autonomous car driving along a road, that car is always going to encounter different obstacles as it goes along. Some of them it might know about, where it might know its route and it'll know it'll have to turn at different points, or something could fall out in front of the car and it has to stop, or a traffic light might change and it'll have to react to that. But for this example, let's say the car is driving along the road and it identifies a sign that says there's a corner ahead. So it knows there's a corner coming up, and it'll kind of say, right, well, by the time I reach that corner, I'll want to know how much I need to turn the wheels to make that corner, and how much power I should apply to the wheels when I'm turning them, so that I definitely make it around that corner. So it has a deadline, and it has a task, which is make those calculations. So it needs to make sure that that task is completed before the deadline. But let's say for some reason the car gets busy. Let's say you're messing with the media center in the car and you're trying to change the song on that, and that takes up enough of the car's time that it goes, right, I've been too busy now to actually make the calculation to turn the wheels and how much I should power them by, and we've actually reached this corner, so I've missed my deadline. So in that case, the system's failed. And like if we're talking about an autonomous car, you never want it to miss the deadline of calculating when it should turn around a corner. So that's a very good hard real-time requirement, is that we have our deadline, we need to meet it, and we know when we need to meet it by. And if we miss that deadline, even by the smallest amount, we could have overshot a corner. So we can never meet or never miss our hard real-time deadlines. So let's have a look at that with our pictures. So we have our car driving along. It's set a deadline because it's identified, oh, there's a corner coming up in a few hundred meters that I'm going to have to deal with. So it says, by this deadline, I need to know what I'm doing to deal with that corner. And unfortunately, it missed its deadline, it didn't turn the corner properly, and it actually impacted this sign. Now thankfully, we could say there's a really good hard real-time requirement that if this car in any way goes off the road, or isn't exactly where it needs to be on the road, that the brakes come on straight away. So thankfully everyone in this car was fine, but in this case, we didn't make our calculation in time, we haven't really turned the corner properly, and we've gone off the road. We can definitely say this is a system failure. And that's down to the fact that we missed a hard real-time requirement. So let's have a look at high-performance real-time and where the difference is there. So let's start off by looking at a firm real-time requirement in this context. So with our car, if we missed any hard deadline or hard real-time requirement, then we had a system failure. In the case of this drone, or in the case of this example, we have a drone. So this drone is going to be flying about above our farm here, keeping an eye on the fields for us, because let's say we have a tractor going around ploughing the fields and we want to make sure that everything's going well and have some data back at our farm headquarters. So we have this drone flying around, it's constantly figuring out how much power to give to the propellers and keep itself level. And its feature is that it has a camera. So it's going to send us back video stream at 30 frames per second, showing us exactly what's going on our farm where that drone's flying around. And we're going to be sitting in our control center, keeping an eye on this. So that's our system. Let's say Unfortunately for the drone, it gets a bit busy. Let's say there's a bit of wind, so it's spending some extra time trying to compensate for the wind and make sure that its propellers are going at the right speed and it's stayed level, so you still get some accurate video shots. You know, the camera isn't pointed off at kind of the wrong angle or anything like that. And because it's spending that extra bit of time making sure that everything's right, it has to drop a few frames of video. So our requirement was that we receive the video at 30 frames per second. But let's say the drone has to go, no, I'm sorry, I can't do that, but I have to drop 1 in every 300 frames to make sure that I keep meeting my own hard requirements of not flipping over, or, you know, not overpowering one of the propellers so that I flip to one side or anything like that. So it's dropped a frame every 300, or 1 frame in every 300. So then we go from 30 frames a second down to 29. And that's not, we might not even notice that sitting in the control room. In terms of the quality of the video, 29 frames per second is probably not going to mean that we're going to miss anything. So the system hasn't failed yet. You know, it's missed the deadline, or it's pushed the deadline, but it hasn't actually really jumped over the line on the deadline and completely missed it. So what happens then if things get a bit worse? Let's say there's a flock of birds that have now flown over and the drone is in the middle of the flock of birds trying to avoid them, so it's really busy, constantly having to fly and avoid these birds. So it's still supposed to send video at 30 frames per second, but unfortunately then, because of how busy it is, it goes down and it drops 1 in every 3 frames. Then we end up losing a third of our video stream, which we would probably see back in the control room. We're down to 20 frames per second. And that might actually impact us enough that we could say, well, hold on, this system's failed because it's no longer able to send at 30 frames per second, but it's not even able to send a high enough quality of video back that we can tolerate the fact that it's not sending the 30 frames per second. So that would be a failure for our firm real-time requirement. So that's our 2. So we've had the hard real-time requirement so far, where we can't miss the deadline at all because, you know, we don't want to drive into that corner. We've the firm real-time requirement where we're going, okay, we can push this a bit, where we can let the video stream degrade somewhat and still not fail, but we'll reach a point where it's not good enough and the system has failed. So let's have a look at the final requirement, which is a soft real-time requirement. So let's stick with the drone for now. So it's still flying around above the farm, keeping an eye on things for us. And it still has a camera on it, sending back the video at 30 frames per second. But let's say we've upgraded the drone, and we've added in this new feature, which is this little weather sensor. So it's going to gather temperature data and the wind speed and maybe the air quality, and send them back to us. And it's going to send them back with a soft requirement of sending the data back every second. So we've 2 requirements. We've the 30 frames of video per second and the weather data every 1 second. So let's say again the drone gets busy. There's another bird that's flying around causing it a bit of hassle. And then it's kind of said, right, I'm spending extra time trying to avoid this bird. I cannot send weather data every second. And it says, I'm going to send the weather data every 5 seconds because I need to send video at 30 frames per second, and that's a firm requirement, which is more important than the soft requirement. So the system might go from sending weather data every 1 second to every 5, but we wouldn't consider that a system failure because we're still meeting our firm requirements. It's just the soft requirement that's been pushed out. But let's take it a little bit further again, and let's say that we reach a point where we actually can't send the weather data at all, because the system is just so busy. But we're still able to send video at 30 frames per second. So we have no weather data coming back because the drone has unfortunately ended up inside this flock of birds that it cannot get out of, and it's too busy trying to avoid all of them to send the weather data, but it can still send the video. Well, then we might actually say that this is still not a failure because we're still meeting that firm requirement. We haven't pushed it at all. Our video is still coming back at 30 frames per second. We've just had to drop our soft requirement of sending back the weather data. And that's kind of all three of our different areas. We have the hard real-time requirements of deadlines that cannot be missed and must be completed within a certain amount of time, or the system has failed. Then we have the firm deadlines that can be pushed a little bit. You have some wiggle room, but if you push them too much, the system will fail. And then you have your soft requirements, which are very nice to have, but if you have to, at the end of the day, you can push out that soft requirement a little bit to make sure that you still meet your firm and your hard requirements. So that's where they come in. So one big thing that kind of comes up throughout all of this is that you've got kind of a task that you'll have to complete, and you'll have a time that it'll have to be completed by. We've got shown up here the two blue bars, or the bar on the top, let's say, is time going from left to right. And at some point during that time, we'll have to complete a task, and we'll have a deadline for finishing that off. So this could be our car driving along the road, that it's going to realize there's a corner coming up. Know it's got to complete the task of figuring out how to turn that corner, and it knows it has to complete it by the time it reaches the corner. And so if we've no other tasks in the queue, for whatever reason we're driving along and the car doesn't have anything else to do, we can just very quickly complete the task. Or we could put it off for a little while and still have plenty of time to complete it. Or slightly more realistically, we might have a few other tasks that we need to complete, so we add our task onto the queue. There's still plenty of time to get it done, so that's great. We have no issues. We have issues come up when maybe we have a task that's going to take a certain amount of time to complete, but occasionally we could get a deadline for it that's way too small to actually complete the task. So even if we immediately start trying to execute this task, once we know that we have to do it, we might not even have enough time to get it done before we start. So what can we really do about this? We can't, unfortunately, control the task deadline. Let's say this is the autonomous car and someone has run out in front of the car and we need to slam on the brakes. We unfortunately can't add any distance between us and them once they run out in front of us. We can't make ourselves further away, and we can't instantaneously make ourselves slower without hitting the brakes. So either way, we have to complete this task, which is put on the brakes. So we can't control the deadline. All we can do is try and make sure that when we have to execute this task, that we will execute it in the shortest amount of time possible. And there's a few things we can do that are going to help us influence that. So one thing we can do is relocate some of our code. So if we have a look at this diagram where we have our heart and our different caches. Now, this shows a single core system. If we're talking about PolarFire SoC, obviously we've more than one core available. So we'll talk about that a bit more in a minute. But for now, let's just think about things in a single core way. So we have our heart, and it could take us 5 to 10 cycles to complete an instruction. So let's say it's going to take 10 cycles to complete that instruction because, it's a handy round number to choose, and we don't want to go with a variable amount of time. Let's just always expect that this will take the longest amount of time possible to complete. So then we have an L1 cache. So let's say we check and see if our instruction we need to complete is in the L1 cache. So it could take us 5 cycles to do that. And if it's not in the L1, it'll take us another 10 cycles to go out to the L2 cache and check if our instruction is there. And let's say if we get to the L2 cache, we don't have the instruction there. It's going to take us another 20 cycles to actually go and fetch it from DDR. So if we add all of that up, we're talking about 10 cycles to complete an instruction, 5 cycles to fetch it if it's in the L1, let's assume it's not, 10 cycles to fetch it from the L2, and let's assume it's not, and then another 20 to get it from the DDR. And now actually one thing just to mention is these numbers aren't accurate for PolarFire SoC. They're just some very nice round numbers that I used for illustration. PolarFire SoC obviously does have the heart, the L1 cache, the L2 cache, and have a DDR controller. But these numbers are just for illustration. So back to the point. If it takes us 10 cycles to complete the instruction and then another 35 cycles to fetch it. We're talking about 45 cycles per instruction to actually complete them. And if we had 100 instructions that we had to complete for our task, let's say it was the interrupt handler for someone hitting the brake pedal, and it was 100 instructions to cause the brakes to be applied, well, then we're talking about 450 cycles to actually complete all of those things and have our task done and meet its deadline. Let's say our deadline is 250 cycles. Then we're going to miss our deadline and our system is going to fail. So what we could do is try and move the interrupt handler for that brake pedal being applied from the DDR so that it's stored somewhere a bit closer to the heart, so maybe it takes a bit less time to fetch. So what we can do is we can convert some of our L2 cache into a LIM, or loosely integrated memory. And it's loosely integrated because it's the L2 cache, it's a little bit further from the heart. You can convert some of the L1 cache into what's called a TIM, or tightly integrated memory, and I'll talk about that in a minute. But let's say we move the interrupt handler for our brake pedal being applied into the L2 cache, or into the LIM, which we created from the L2 cache. But then we're talking about 10 cycles to complete the instruction once we have it, 5 cycles to go through the L1, and then 10 cycles to go to the LIM. So we've gone to 25 cycles. And again, we have 100 instructions, so we're at 250 cycles to complete our task, down from 450. So that means that our task, or our time to complete our task, very nicely now fits inside our task deadline. And we're no longer going to potentially overshoot this task. So that's one thing we can do to actually try and reduce the amount of time it'll take us to complete our tasks. But as I mentioned a minute ago, that example was talking about a single core. How can we reduce the amount of time it'll take us to complete this task when we use one heart? Well, in PolarFire SoC, we actually have a few application cores. We have 4 of them. So if we have 4 tasks lined up, now this is a very nice setup because all of our tasks are going to complete within our deadline. But let's say we have 4 tasks lined up. These are going to happen sequentially in this setup. But if we bring in heart 2, we could split it up so that our tasks are executed between heart 1 and heart 2. We could bring in heart 3 and give it one of the tasks, and we could bring in heart 4 and give it one of the tasks. And suddenly we've gone from a system where we had 4 tasks that were going to execute sequentially on heart 1 to a system where we have 4 tasks that are going to execute in parallel across all 4 of the hearts. Now obviously this is only possible if the tasks are all independent and the result of one task isn't being used in the next task. But it is possible that we can partition our work between our different cores to make sure that we have as much time as possible on each heart to deal with whatever tasks come up and get allocated to them. And there's one other situation I'd like to talk about before we finish up, and that is determinism. So we've kind of touched on this a little bit, but we haven't really dealt with it yet. So let's go back to the example of the car driving down the road. So in this case, the car is not driving autonomously, and it's got an electronic braking system. So let's say we've spotted a corner in the distance, and we've actually got to say, oh, hold on, I need to stop for that corner. I'm going way too fast. I need to slam on the brakes and make sure I stop in time. So the brake pedal's applied on the car. So let's say we're kind of in the situation where 99% of the time, when you push the brake pedal, the brakes are going to be applied in the green amount of time down at the bottom. So they'll be applied within the task deadline, and your car will not overshoot where you want it to stop. And let's say another 0.99% of the time, the brakes will be applied within the green and yellow time to complete task shown down there, well then we're still okay. The brakes will be applied within the task deadline, so we haven't overshot it. You know, it's not ideal. We don't want the brakes to take that long to be applied, but we can deal with it. But then let's say there's like a 0.01% of the time that it might take the brakes that little bit longer to be applied, and that results in the car overshooting and the brakes being applied and impacting this corner. Well, then we have a system failure, and it could be that we have our code optimized as much as possible, that the time to complete a task is shrunk down as much as we can make it, but we've still ended up overshooting it a bit, and that could be because we weren't deterministic in how that task was completed. So if we have a look at this slide here, where we have our SMP system, where our actual application or our system is running across all 4 hearts, running the same application. And they all have their L1 cache. Individually, they have the shared L2 cache and the shared DDR. And then we have our little graph here showing the execution time variability for a different chunk of code. So this is like our brake pedal being applied. You know, once we push that brake pedal, we want our brake pedal or our brake applying code to execute. And it could be that, for example, it executes and takes one of the lowest amount of times shown here, and then the brakes are applied in the perfect amount of time. But it could be that we apply the brakes and it takes one of the higher peaks here for the code to execute, and it means then that we've missed our task deadline. So really we don't want to see a graph with any kind of variability at all. We'd like to see a nice static graph. Well, how do we do that? What you can do is take one of the hearts out of that SMP system. So then your SMP system is only running on 3 hearts. So for example, that could be Linux running and doing whatever its job is within the system. So those 3 SMP hearts will still have their L1 cache, they'll still have the shared L2, and they'll still have access to the shared DDR. But then that 4th heart that you took out of the SMP system, you can actually allocate that as a real-time heart. And you can convert its L1 cache into a TIM, or a tightly integrated memory, so you have some code storage really close to the actual heart itself. And then you can take a chunk out of the L2 cache and use that as LIM, which is the loosely integrated memory. And then the real-time heart can execute out of those memory locations, so that when, let's say, an interrupt comes in to apply the brakes, this real-time heart will have it'll have deterministic access to its instructions. So the execution time variability goes down to static. And that means that when our car is driving along the road, we never end up in the situation where it could take too long to apply the brakes. They will always deterministically be applied in the same amount of time. So thank you all very much for attending this session on hard real-time versus high-performance real-time. I hope you found it beneficial, and please do make sure to stop by the Microchip booth for more information on our products and PolarFire SoC.